treat monomials or like terms. Okay, so in the past we've had, say, for example, 4a plus 2a, and that gave us 6a. Or, you know, maybe 7x minus 4x to get 3x. You treat a radical expression the same way you treat the square root the same way you treat a variable. So they're like terms. So if I have 4 times the square root of 3 plus 2 times the square root of 3, I'm going to add the 4 and the 2, and I keep the square root of 3 the same way I would have an x. Or if I had, for example, 7 times the square root of 2 minus 4 times the square root of 2, I subtract and hold on to the square root of 2. Okay. So we collect like terms. So if I have, say, for example, 3 times the square root of 2 plus 4 times the square root of 6, these don't match. Because they don't match, I can't add them. This would be the same as if I tried to add 3y plus 4x. I can't add those, so I can't add these. They have to match. Okay, so if we're going to simplify expressions, we're collecting our like terms. So if I have 5 times the square root of 2 plus 7 times the square root of 2 minus 6 times the square root of 2. Well, 5 plus 7 is 12. And then if I subtract 6 from 12, I get 6. Okay, here I have 10 times the square root of 7 plus 5 times the square root of 11 plus 4 times the square root of 7 minus 6 times the square root of 11. I have 7s and I have 11s. I can only combine the likes. So I'm going to rewrite them next to each other. You don't have to do that, but some people find that easier. So 10 plus 4 is 14 times the square root of 7. 5 minus 6 is negative 1 times the square root of 11, but in the same way that you don't put the 1 in front of a variable, you don't have to put the 1 in front of the root either. Here I only have 2 like terms, so I combine those, and then my non-like term just hangs out. Okay, sometimes we have unlike radicands. Okay, and if you'll remember, the radicand is the part that's underneath the radical So we're saying that these don't match. Okay, so when this happens, we have to try to make them match. Okay, so our first step is to try to make the radicants match. Try to make them like terms. Okay, so 18 is 2 times 9, and 9 is 2 times 3, or sorry, 3 times 3. Yeah, on Mars it's 2 times 3, but here it's 3 times 3. So I have a matching pair of 3's that I can bring outside. So I'll bring that 3 out, and then I have this 2 that's been left behind. So that stays inside. And so this 2 times the square root of 18 becomes 6 times the square root of 2. Okay. Now I'm going to try my 32, and I get 2 times 16, which is 2 times 8, which is 2 times 4, which is 2 times 2. I have 2 sets of 2 with the 2 left over. So I can bring out one of each of these. There was already a 2 there, and then I bring out 2 2's from each pair, and then there's a 2 left over. So this 2 times the square root of 32 is now 8 times the square root of 2. So I'm just going to rewrite these down here. And then I'm going to take my 72, which is 2 times 36, and 36 is 2 times 18, and 18 is 2 times 9, and 9 is 3 times 3. I have a pair of 2's, and I have a pair of 3's with the 2 left over. So I can bring out that 2 and that 3 from my matching pairs and leave the 2 behind. So that gives me 6 times the square root of 2. And now I have like terms that I can add together. So 6 plus 8 is 14, plus 6 is 20. Now, of course, you don't have to do a factor tree. If you know that 18 is 2 times 9, I can pull the square root of that 9 out. So you can just use your knowledge of perfect squares. You don't have to do a factor tree. If you know that 32 is 2 times 16, you can pull the square root of the 16 out. And then 72 is 2 times 36. Oops. And 36, of course, is a perfect square. So, there's still this method. Okay, and then of course step 2 was to add like terms. If you need to write that in there. Okay, so if I have I'm going to use both factor trees and perfect squares in the same problem at the same time. because here I know that 45 is 9 times 5. And I know that 9 is a perfect square. So the square root of 9 is 3. So this 3 came from the 9, and that 3 was just already there. So this is going to give me 9 times the square root of 5. 20, I know, is 4 times 5, and this is a perfect square. So this is 2 times the square root of 5. Now 245. Right now I've got 5s as my remaining radicand. So I can use that knowledge and find out that 245 is 5 times 49, and then 49 is a perfect square. Or if I don't think of that, I can start here and get to the same place. So now I have my new simplified terms. So I had 9 root 5 plus 2 times the square root of 5 plus 7 times the square root of 5. And just make sure you keep these the same. If it's plus, it's plus. If it's minus, it's minus. So 9 plus 2 is 11, plus 7 is 18. Alright, so now we have multiplying Now, do you remember if I said 2x times 3y, we multiplied the 2 and the 3 to get 6, and then we multiply the x and the y? So this is kind of the same idea. If I have 3 times the square root of 2 times 2 times the square root of 6, I'm going to multiply the 3 and the 2, and then I'm going to multiply the square root of 2 and the square root of 6. So 3 times 2, and then times the square root of 2 times the square root of 6. So that's going to give me 6 times the square root of 12. Now once I get here, I need to see if this new radicand will reduce. 12 is 3 times 4, and 4 is a perfect square. So the square root of 4 is 2. There's a 3 left over. So it ends up being 12 times the square root of 3. Okay, so for another example, if I take 9 times the square root of 5 times 11 times the square root of 15. Okay, I'm going to do 9 times 11 and the square root of 5 times the square root of 15. 9 times 11, that's easy, that's 99. And then 5 times 15 is 75. And then I need to check this 75 and see what I can bring out of it. Well, because I know money, I know that 75 cents is 3/4. And then 25 is 5 times 5, which, you know, it's a perfect square. So I can bring that 5 out. And I have 99 times 5. This 3 gets left behind. So I have 495 times the square root of 3. Okay, and we'll do one more. like this. Okay, so 2 times 7 and then the square root of 6 times the square root of 3. 2 times 7 is 14. 6 times 3 is 18. 18 is 2 times 9. And 9 is 3 times 3. So I can bring that 3 out, and the 2 remains. And 14 times 3. Everybody's memorized their 14s by now, right? No? Okay, 14 times 3 is 42 times the square root of 2. Now we have another kind of multiplying. This is distribution. It's the same as the multiplying we just did, except you do it twice. So if I have 3 times the square root of 5 times 2 times the square root of 5 plus 5 times the square root of 3. I'm going to distribute this, which means I'm going to multiply it by both of these terms. So this is 3 times the square root of 5 times 2 times the square root of 5 plus 3 times the square root of 5 times 5 times the square root of 3. So that's 3 times 2 times the square root of 5 times the square root of 5. Now what happens when I multiply a square root by itself? Technically what happens is I get the square root of 25, which is just 5. So if you have two identical radicals with identical radicands underneath them and you multiply them together, the radicals cancel each other out and you're just left with whatever number is underneath, so 5. And then here I have 3 times 5 times the square root of 5 times the square root of 3. So that's 15 times the square root of 15. 15 is just 3 times 5, so I don't have any perfect squares in here, right? So this becomes 30 plus 15 times the square root of 15. And you don't have to do anything with that, like factor anything back out of the 30 and the 15. You're good, you're done. Let's do 3 times the square root of 2, 4 times the square root of 3 plus 6 times the square root of 2. Right? So I'm going to distribute this times both of those. So I'm going to multiply my 3 times my 4 and my square root of 2 times my square root of 3, which is going to give me 12 times the square root of 6. And then I'm going to multiply my 3 times my 6, which is going to give me 18. But then my square root of 2 times the square root of 2 is going to cancel each other out and just give me a 2. And that's 36. And 6 is 2 times 3. There are no perfect squares inside of a 6. So that's small. Now I do want to show you, you don't have to write those middle steps. Okay? If it's possible, I mean, if you're comfortable with this, you can do this in your head. And I can say, okay, that's 15 and then 6. Right? So 5 times 3, 15, 3 times 2, 6. And then 5 times 1 is 5, and then the square root of 3 times the square root of 3 cancel each other out. So, you know, you can do this without having to write in this central step. I mean, I know what they look like. I don't know all of them. And we are going to talk about multiplying radical expressions. But this time we have two binomials. And we have our good friend FOIL coming back. And in case you forgot, that's first, outside, inside, last. So if I want to multiply 5 times the square root of 2 minus the square root of 3 times the square root of 5 plus 4 times the square root of 3. Multiply first, so that's going to give me 5 times the square root of 2 times the square root of 5. And then I do outside, which is going to give me 5 times 4 times the square root of 2 times the square root of 3. And then I'm going to do inside, which is the square root of 3 times the square root of 5. And, oh, that looks like the same color. Hold on. And last, which is the square root of 3 times, let me rewrite that. Hold on. So I have 4 times 1 times the square root of 3 times the square root of 3. This gives us 5 times the square root of 10 plus 20 times the square root of 6 minus the square root of 15 minus 4 times 3. Okay. 10 has no perfect squares, so I can't simplify that. 6, no perfect squares. 15, no perfect squares. So the only thing I can really do is multiply that 4 and 3. And then you're done. I know it's really long looking and you're used to simplifying things to be smaller than this, but you can't combine any of these. So that's the correct answer. Okay, this will come up in area problems. Okay, so we have the area of a triangle. Is 1/2 base times height, right? And if my height is 4 root 3 plus root 5, and my base is 2 root 3 plus root 5, and I want to find the area of this triangle. So it's 1/2 of the base and the height multiplied together. Okay, so I'm going to FOIL this. So that's going to be 8 times 3, right? Because I have 4 times 2 gives me 8, and then the square roots cancel each other out. And then that is going to be 4 times the square root of 15, because the 3 times 5 is 15. And then I'm going to have 2 times the square root of 15. And finally, my square roots of 5 are going to cancel each other out and leave me with just a 5. Well, 8 times 3 is 24, right? So that's 24. Plus 5 is 29. And then 4 times the square root of 15 plus 2 times the square root of 15 is 6 root 15. And now 1/2 times is the same thing as divide by 2. So 29 divided by 2 is 14.5. And 6 divided by 2 is 3. And you only divide your coefficient, not your root. So your area is 14.5 plus 3 times the square root of 15. And that's your answer.